Hello everyone, welcome to the video lecture of this course finite element method. So this is the fourth module that we are discussing right now, and this module actually deals with the two-dimensional vector variable problems. So earlier in this lecture we have discussed the concept of the elasticity equations, and there we have seen four basic sets of the elasticity equations like strain displacement, then stress strain relationship, and equilibrium equations, constitutive equations. So all these equations we have discussed in details. Then we have discussed the concept of the axisymmetric elements, and there we have discussed different formula for these axisymmetric elements like the stress strain relationship matrix, then strain displacement matrix, then stiffness matrix, and based on all this formula different numericals also we have discussed earlier. Now in the last lecture we have discussed the concept of the plate theory. So there we have seen the classification of the plate theory like the thin plate and thick plate, and this is basically classified based on the thickness to width ratio of the different plate element. And we have actually discussed the thin plate theory in details in the last lecture, and there we have seen that the Kirchhoff's plate theory it is applicable for the thin plate theory, and in case of the thick plate theory actually the Mendlin theory it is applicable. But in case of the thin plate theory that we have discussed in the last lecture, there are different notifications, then the basic equations for this thin plate theory, then how to calculate the moment and shear forces for this thin plate theory, then the different boundary conditions that we need to consider for this thin plate theory analysis. All these things were discussed in details in the last lecture. Now today in this lecture we will discuss the thick plate theory in details, and after that several short type questions will be discussed regarding the different topics that we have covered till now in this finite element method. Okay, so let us start this lecture. So these are the course objectives and course outcomes of this subject finite element method. So these are known to us already, and this is the COPO mapping for this subject. So we will start from this slide. So here we will discuss the concept of the thick plate theory in details, and from our concept of the plate we know that a plate is actually a planar structure with a very small thickness in comparison to the planar dimension. So this is the concept of the plate, and the forces which are applied on a plate, these are actually perpendicular to the plane of the plate, and therefore the plate tries to resist the applied forces by means of bending in two direction and the twisting moment. Now this plate theory it actually takes the advantage of this disparity in length scale to reduce the full length three-dimensional solid mechanics problem into the two-dimensional problem. And in case of the thin plate theory we have seen earlier there are three different assumptions in case of the Kirchhoff's theory we have taken to simplify the three-dimensional problem into two-dimensional problem. Now the aim of this plate theory it is actually to calculate the deformation and the stresses in a plate subjected to loads. That means when different loads or forces will be applied perpendicular to the plane of the plate, then the amount of the deformation and the stresses that will be occurring on the plate element that will be calculated, and which is the main aim of this plate theory. Now, a flat plate like a straight beam, it carries lateral load by bending. So this is one example. And the analysis of the plates, these are actually categorized into two types based on the thickness to breadth ratio. And the classification is like thick plate and thin plate analysis. So in the last lecture, we have discussed the thin plate theory in details, and we have seen that if the thickness to width ratio, the thickness to breadth ratio of the plate is less than 0.1 and the maximum deflection is less than 1/10 of thickness, in that case the plate is classified as the thin plate. And the Kirchhoff's plate theory regarding its three different assumptions, uh, it were discussed in details in the last lecture. But in case of this thick plate theory, the Mindlin plate theory is actually used, and where the effect of the shear deformation is included. So today in this lecture we will discuss the concept of this thick plate theory and the Mindlin thick plate theory in details. Now, although this Kirchhoff's hypothesis or the Kirchhoff's plate theory provides comparatively simple analytical solution for most of the cases, but there are certain limitations of this Kirchhoff's plate theory which are mainly applicable to the thin plate elements or thin plate structure. Like this Kirchhoff's plate element, it cannot rotate independently of the position of the mid surface. And as a result of this, problems occur at the boundaries where the undefined transverse shear stresses are necessarily, especially for thick plates. So this is one limitation that it cannot, that the limitation of this Kirchhoff's plate theory is that it cannot rotate independently of the position of the mid surface. So problems occur at the boundaries where the undefined transverse shear stresses are necessary, and which is actually required for the thick plate. Again, this Kirchhoff's plate theory is only applicable for analysis of plates with smaller deformations, as higher order terms of strain displacement relationship cannot be neglected for large deformation. Again, as plate deflects its transverse stiffness, it gets changed. So only for small deformations the transverse stiffness can be assumed to be constant. So this is one more limitation of this Kirchhoff's theory, that it is only applicable for analysis of plates with smaller deformations. So as there are two different limitations for the Kirchhoff's plate theory, then for the thick plate theory we consider the Mindlin plate theory, which is also known as the Reisner-Mindlin plate theory. So this Reisner-Mindlin plate theory, it is actually applied for analysis of thick plates where the shear deformation are considered and rotation and lateral deflections are decoupled. So in case of this thick plate theory, we use the Reisner-Mindlin plate theory where the shear deformations, these are considered, and the rotation and the lateral deflections, these are decoupled. Now, it does not require the cross section to be perpendicular to the axial forces after deformation. So it was one of the assumption of the Kirchhoff's theory, which is not required in case of this Mindlin plate theory. And now there are certain limitations or certain assumption actually for this Reisner-Mindlin plate theory, which we can refer from this diagram, that is the bending of the thick plate. We can see here there are three different assumptions that we need to consider, and this Mindlin plate theory, it actually based on the three different assumptions like the deflections of the plate are small. This is number one assumption, that in case of the thick plate theory, the deflections are small. The number two assumption is that the normal to the plate mid surface before deformation remains straight but is not necessarily normal to it after deformation. So which we have seen earlier in case of the Kirchhoff's theory, that before bending and after bending it remains straight, but here the normal to the plate mid surface before deformation remains straight, but it is not necessarily normal to it after the deformation. And the third assumption is that the stresses normal to the mid surface are negligible. So these are the three assumptions which you can see here. These are applicable for this Reisner-Mendlin plate theory. So according to this Reisner-Mendlin plate theory, the deformation parallel to the undeformed mid surface u and v at a distance z from the centroidal axis are expressed by u equals to z theta y and v equals to minus z theta x. These are the equation for u and v at a distance z from the centroidal axis. Here the theta x and theta y, these are the rotations of the line normal to the neutral axis of the plate with respect to the x and y axis respectively before deformation. Now the curvatures in case of this bending of the thick plate, these are expressed by lambda x, this is equals to del theta y del x, and lambda y, this is equals to minus del theta x del y. In the similar manner, the twist for the plate, it is actually given by lambda xy, this is equals to del theta y del y minus del theta x del x. Now we know that the bending stresses for the plate m equals to T matrix multiplied by the lambda matrix, and the bending stresses for the plate m equals to a column matrix of mx, my and mxy. So this is equals to the D matrix, which is actually et cube divided by 12 into 1 minus nu square multiplied by 3 by 3 matrix where the Poisson's ratio are there, and multiplied by a column matrix for the lambda, which is lambda x, lambda y and lambda xy. Let the transverse shear strains are gamma xz, this is equals to theta y plus del w del x, and gamma yz, this is equals to minus theta x plus del w del y. So these are the equations for the bending stress, then the twist, then the transverse shear strain for this bending of the thick plate. And the shear strain energy, it can be expressed u equals to half alpha Ga double integration over a gamma x square plus gamma y square dx dy. So here instead of gamma x and gamma y, we can put the values that we have seen earlier. And finally we are getting the equation number 4.126. Here G is equals to E divided by 2 into 1 plus nu. E is the Young's modulus and nu is the Poisson's ratio. So these are the concept of the thick plate, and corresponding to this thick plate, the Reisner-Mendlin plate theory. And regarding this plate theory, that is the bending of the thick plate, the formula for the twist, then the bending stresses, then the transverse shear strain and shear strain energy, these are discussed now. So Now we will discuss some short questions or some short definition regarding the different topics of this finite element method that we have covered till now. So till now actually we have covered the 4 different modules. At first module we have discussed the introduction part of this finite element method. And in the second module we have discussed the one-dimensional problems. And in the third module we have discussed the two-dimensional scalar variable problems, and in the fourth module we are discussing these two-dimensional vector variable problems. So different questions regarding these 4 different modules we will discuss just now. That is, first we are having the definition of the axisymmetric element. So this definition we have discussed in this fourth module only. That is, many three-dimensional problems in engineering exhibit symmetry about an axis of rotation, and such type of problems are solved by a special two-dimensional element called an axisymmetric element. So this concept of the axisymmetric element is known to us, and based on this concept of the axisymmetric element we have seen different formula in this module for the strain displacement matrix, then stress strain relationship matrix, then stiffness matrix. And based on this different formula we have discussed number of numericals which are a bit lengthy, and the matrix operations like especially the matrix multiplication were required to solve those numericals. Now, what are the conditions for a problem to be axisymmetric? Now, there are 3 different conditions, like the problem domain must be symmetric about the axis of revolution, then all boundary conditions must be symmetric about the axis of revolution, and all loading conditions must be symmetric about the axis of revolution. So these are the 3 different conditions for a problem to be axisymmetric. Next we are having the question to write down a formula for the displacement equation for an axisymmetric triangular element. So this is the formula for the displacement function, that is urz, as we consider the cylindrical concept, that is rz theta, and urz and wrz, that column matrix, equals to a 2/6 matrix multiplied by a column matrix of u1 w1 u2 w2 u3 w3. So this formula is known to us. This n is the shape function. So this formula we have also earlier used to solve different numericals based on the axisymmetric triangular element. Next, the question is to write the shape functions for an axisymmetric triangular element. And these are the formula for the shape function for an axisymmetric triangular element, like n1 is alpha 1 plus beta 1 r plus alpha gamma 1 z by 2 I say. Then n2 is alpha 2 plus beta 2 r plus gamma 2 z by 2 I say. And n3 is alpha 3 plus beta 3 r plus gamma 3 z by 2 I say. Now, the formula for this alpha 1 beta 1 gamma 1 alpha 2 beta 2 gamma 2 and alpha 3 beta 3 gamma 3, these are written here. So to apply the formula of the shape function in an n numerical, that is n1 n2 and n3, we need to remember the formula of this shape function as well as the parameters alpha 1 beta 1 gamma 1, all these things. So this type of complicated formulas are there in this chapter, so a lot of practices are required actually to remember such formula. Next, in this question we need to write the strain displacement matrix equation for an axisymmetric triangular element. So this is the formula for the strain displacement matrix. It is B equals to 1 by 2 A multiplied by a 4/6 matrix, and here this A, it is the area of that triangular element. Now based on the type of the numerical we need to use the formula, that is this formula for to calculate the area of the triangular element. There is one formula based on the 3 by 3 matrix, and another formula is that simple formula half into the width into height, or you can say half into base into height. That formula to calculate the area of that triangle, that is the axisymmetric triangular element. And the coordinate r1, r2 and r3, these are also required here to calculate the value of the coordinate r and z. It is to calculate r, we need to use r1 plus r2 plus r3 by 3, and to calculate z, the formula is z1 plus z2 plus z3 divided by 3. Next we are having one more formula, that is the stress strain relationship matrix, that is D equals to E by 1 plus nu into 1 minus 2V multiplied by a 4 by 4 matrix. So in this matrix we are having the Young's modulus and the Poisson's ratio. So all these formulas also actually we have used to solve different numericals. The procedure to solve those numericals, these are not very complex. The important part is to remember these formulas, which are not very easy. And again I am saying that a lot of practices are required to solve such numericals. A similar type of new formula for this strain displacement matrix, then stress strain relationship matrix, then for the stiffness matrix we will get for the one-dimensional, two-dimensional scalar and two-dimensional vector. And in the next module for isoparametric elements also we will get such type of formula. The next question, it is related to the stiffness matrix equation for an axisymmetric triangular element, and the formula to calculate the stiffness matrix, it is the K matrix equals to 2 pi RA multiplied by the B matrix transpose, then D matrix multiplied by the B matrix, where the coordinate R equals to R1 plus R2 plus R3 divided by 3, and A is the area of the triangular element matrix. And what are these B and D? This B, it is the strain displacement matrix which we have seen in the earlier slide, and this is the formula of the strain displacement matrix B. And D is the stress strain relationship matrix that we can see in the second question of the slide. So these two are required, these two formulas are required to calculate the stiffness matrix. And there is one part, that is BT, that is the transpose of the B matrix also we need to find. So our next question is, what are the ways in which a three-dimensional problem can be reduced to a two-dimensional approach? So this concept was already discussed earlier, like case of plane stress, one dimension is too small when compared to other two dimension. Like the example is gear, where the thickness is small. Next, for plane strain, one dimension is too large when compared to other two dimension. Like the example is long pipe, here the length is very long compared to the diameter of the pipe. And in case of the axisymmetric, the geometry is symmetric about the axis. Example is the cooling tower, where we are having a symmetric geometrical shape. So these are the steps, these are the ways using which a three-dimensional problem can be reduced to a two-dimensional approach. That means we are neglecting the dimension which is comparatively smaller compared to the other two dimensions. Like in case of gear, we have neglected the thickness which is small. Next, in case of the long pipe, the length is actually long compared to the diameter. And in case of the cooling tower, that is in case of the axisymmetric, the geometry is symmetric about the axis. Now there is one small problem, it is given to calculate the Jacobian of the transformation J for the triangular element shown in this figure. So you can see one triangular element is shown and the coordinates are given, like for corresponding to node 1 we are having R1 and Z1, like R1 is 2, Z1 is 3. And corresponding to node 2, we are having R2 is 5 and Z2 is 3. And corresponding to node 3, we are having R3 is 3 and Z3 is 6. So these are the coordinates corresponding to the three different nodes for this triangular element is given in this figure. So we need to find the Jacobian matrix. So the formula for the Jacobian matrix, it is directly written here. It is R1 minus R3, then Z1 minus Z3, then R2 minus R3 and Z2 minus Z3. So this is the formula for the Jacobian matrix, and we have entered the necessary values in this Jacobian matrix, and finally we have got and we have calculated the value of the Jacobian matrix, which is coming as 9 unit. So the calculation for this Jacobian matrix, it is also discussed earlier. So here one simple example we have discussed again to calculate the Jacobian or Jacobian matrix of any triangular element. Next we have the questions regarding the thin plate element, that is what are the assumptions used in thin plate element. So the line normal to the neutral axis before bending remains straight after bending, and the transverse shearing strains are assumed to be 0, that is the shear strains gamma xz and gamma yz will be 0. So these are the assumptions that we have considered in case of the thin plate element. And one more assumption was there, that is the normal stress in thickness direction is neglected. There were actually three different assumptions for this thin plate theory. Next, what are the assumptions used in case of thick plate element? So in the first lecture we have discussed this assumption in case of this Reisner-Mendlin theory, which is applicable for the thick plate element. So the next question is the three phases of the finite element method. So earlier in the introduction module we have discussed these three phases of this finite element method, like the pre-processing, analysis and the post-processing. These are the basic three steps or the three phases of the finite element modeling, and under these three steps we have discussed the 10 general steps which are actually required for any numerical to solve using this finite element concept. Our next question is, what is structural and non-structural problem? So the finite element method or finite element modeling that we have discussed earlier, there we have seen that the classification of these finite element problems, these are actually structural and non-structural problems. And in case of the structural problems, we actually focus or we actually calculate the displacement at each nodal point, and by using these displacement solutions, stress and strain in each element can be calculated. And in case of the non-structural problems, the temperatures or fluid pressure at each nodal point is obtained, and by using these values properties, different properties such as heat flow, fluid flow, etc. for each element can be calculated. So these are the classification of the finite element modeling problems, like structural and non-structural problem. Our next question is, what are the methods are generally associated with the finite element analysis? So there are actually two methods which are generally associated. One is the force method and another is the displacement or stiffness method. The definitions for these two methods are written, and in case of the force method, internal forces are considered as the unknowns of the problem, and in case of the displacement method, displacements of the nodes are considered as the unknowns of the problem. And this displacement method, it is desirable compared to the force method. Our next question is, why polynomial type of interpolation functions are mostly used in finite element method? And the reasons for choosing this polynomial interpolation functions are it is easy to formulate and computerize the finite element equations, and it is also easy to perform differentiation or integration, and the accuracy of the results can be improved by increasing the order of the polynomial. So these different reasons we have seen while discussing the Rayleigh-Ritz method, how increasing the order of the polynomial, the error can be minimized. We have seen there. Next question is, what is Rayleigh-Ritz method? So it is actually integral approach method which is useful for solving the complex structural problems, and it is possible only if a suitable functional is available. And what is meant by discretization and assemblage? So these are discussed a number of times earlier, that the art of subdividing a complex structure into a convenient number of smaller components is known as the discretization. And the smaller components are actually put together in the process of uniting these various elements together. It is called the assemblage. And the different questions like the degrees of freedom, aspect ratio, these are here and these are already discussed earlier. And what is the constitutive law? So this law, that is the stress strain relations, that sigma equals to D matrix multiplied by the E, that is the strain matrix. This is known as the constitutive law or the stress strain relationship matrix. Then to differentiate between global and local axes. So local axes are established in an element, and since it is in the element level, they change with the change in the orientation of the element. The direction differs from element to element. This is in case of the local axis, and in case of the global axis, these are actually defined for the entire system, and they are same in direction for all the elements, even though the elements are differently oriented. So these are the concept, like the concept of the thick plate theory, then the Mainline plate theory applicable for the thick plate theory we have discussed in this lecture, and after that several important questions regarding the 4 different modules that we have discussed till now. It is again discussed here in this lecture. Some important formula, then how to calculate the Jacobian matrix, some important definitions we have discussed again in this lecture. So this is the end for this lecture, and in the next lecture we will start a new module, that is our module number 5, which deals with the isoparametric elements for 2-dimensional problems. So this is the end for this lecture.